Hey, today we're going to talk about bond energy, one of our last chemistry standards. Let's take a look. So, bond energy is this potential energy, so energy that has potential to be released or absorbed when two atoms or ions are bonded together. So, here's some things to know. Bond strength. Bond energy measures bond strength. So if it takes more energy to break the bond, that bond is stronger than another type that takes less energy to break it. When bonds are broken, the change in bond energy is positive. You have to add energy to break the bonds. When bonds are formed, the change in the bond energy is negative because energy is released when bonds are formed. Endothermic reactions is when energy is absorbed from the surroundings. To us, that would feel cold. This change in bond energy is positive. Exothermic reactions is when energy is given off to the surroundings. Those would feel hot from our perspective, and the change in bond energy is negative. All reactions have bonds that are broken and bonds that are formed. If you think of a chemical reaction, the bonds that are existing in the reactant side need to be broken up, and then they form new bonds to make the products. So, if we just take an example of what we have here, we have a combustion reaction, you might remember, and it releases so much energy for each set of these per mole. So things we know is energy is given off because it's produced as a product, which makes it exothermic, and that the change in bond energy would be negative. So these are all things that we start off with. So we're going to model this in several ways, and you'll get to choose which ones you want to show. So from our chemical equation, we have a chemical system. This is all of the reactants and products. We label the reactants, we label the products, and we are simply illustrating that energy is leaving the chemical system to the surroundings. So that's an example of a model of change in bond energy. Another example is looking at the bonds themselves. So we have our original Lewis structures as reactants. Energy is needed to break the bonds, so now we have intermediate atoms. So if we considered all the atoms by themselves, no longer in molecule form, making our new products and their new bonds. Overall, because of this bond breaking and bond forming, the overall energy difference is energy leaves the system. So it's lost to the surroundings. So you always have energy to break the bonds and energy to form the bonds being released. If we add those together, as you'll see in a future model, this is where we get the idea of energy being leaving the system. A different example, a graphical model. So this is an amount of energy starting with 0, going up to infinity, let's call it, and then starting off before the reaction starts to the end of our reaction. So again, we're labeling reactants and products. We're showing what each of them are. And we're going from a higher energy to a lower energy because energy is being given off to the surroundings. So this is meant to totally incorporate all of these ideas. The last model is a mathematical model. So each bond has been determined to have a set amount of energy when that bond is broken for 1 mole's worth of bonds. So fluorine to fluorine, if we break up 1 mole's worth of molecules, it would release 154 kilojoules per mole. These are amounts you would not memorize, you would be given, and you would utilize in order to do this correctly. So as an example of using those, you have to understand the bonding of each of these, so you need to know the Lewis structures to count up the bonds. It's all of the reactants minus all of the products. or really, it's all of the reactant energy required to break it, plus the opposite, the negative part, in order to do the products. So for example, we have 4 carbon-hydrogen bonds here, each at 413 kilojoules, so 4 times 413. We have 2 double-bonded oxygen. From the chart, those are 495 each, and there's 2. Minus carbon dioxide has 2 bonds of CO, 2 times 799. And there's a 4 total of oxygen-hydrogen bonds at 467 a pop times 4. You use your equations, use your math, and you get your answer that you can see at the bottom if I kind of get off of there. All right, so it's much more together, but some people like showing the mathematical model. Come back for the rest to see an endothermic example so you can have all sides of the equation. See you then.